All right, so up to this point, we saw that the rates of chemical reactions depend on the concentration of reactants, and based on experimental data, we can describe a rate law. Here in the second part of this chapter 12 on chemical kinetics, we are going to see how the order of the reactants depend on the detailed reaction mechanism. And then we're also going to see how the rate law gets affected by the temperature. So a reaction mechanism is the sequence of bond making and bond breaking steps that occur during the conversion of the reactants to products. Sometimes this could be in one step, but most of the times this is in more than one step. Each step in a reaction mechanism is called an elementary step. You could also have an intermediate, which is a species that is produced during a reaction that does not appear in the net equation because it reacts in the subsequent elementary step in the mechanism. So you usually have an intermediate when you have more than one step in the reaction mechanism. So let's see here an example of a reaction mechanism that has more than one step. So in other words, it means that the bonds that are breaking and forming are done on separate steps. So here we have the reaction of hydrogen gas that is reacting with iodine chloride. It forms iodine and hydrogen chloride. So the rate law here is determined experimentally using the method of initial rates. So the rate here is going to be equal to the rate constant times the concentration of hydrogen times the concentration of iodine chloride. Now, based on this rate law, a mechanism has been proposed. So the following reaction mechanism is proposed. We could see that in this reaction mechanism right away that there are two elementary steps, right? So you have here two elementary steps. And so in other words, this reaction does not occur in one step where all the bonds break and form in one step, but it actually occurs in two steps. So first, hydrogen is going to react with one molecule of iodine chloride. This is going to form hydrogen iodide and hydrogen chloride. Now notice that hydrogen iodide is not a product in your overall reaction. In the second step, hydrogen iodide is now going to react with the second molecule of iodine chloride, which is going to form iodine and hydrogen chloride. So now we could say that in this reaction, the intermediate is the hydrogen iodide. So we do have an intermediate, and the intermediate, like I said, is hydrogen chloride. So the intermediate in this reaction is hydrogen iodide. So this is the intermediate, which is formed in the first step and then is used right away in the following step and is consumed, right? So in the overall reaction, when we look at the overall reaction here on top, we don't actually see the hydrogen iodide. So although we cannot deduce the rate law for a chemical reaction by looking at the balanced equation, so remember that the rate laws are basically determined experimentally using the method of initial rates. When we look at the rate laws for elementary steps, right, in a reaction mechanism, we can use that elementary step and look at the coefficients in the elementary step and use that to express the rate law for the elementary step. Again, this is specific for elementary steps. Now, Elementary steps are characterized by the number of molecules that are implicated as reactants in that step. This is called molecularity. All right, so it's the number of molecules as reactant that participate in that elementary step. Now we could have different type of molecularity. We're going to talk about here three. Unimolecular, this is when you have only one reactant. So one molecule of that reactant is a reactant. So we say the reaction is unimolecular, uni for one. So in that case, so we have an example right here. You have a reactant A that forms products. So you have only 1 mole of the reactant A. This is implying that there's only one molecule. So this is unimolecular. And we could say for this elementary step, right? Remember, these are all elementary steps. So in a reaction mechanism, we could say that the rate law for this elementary step could be described as the rate of this elementary step equaling the rate constant times the concentration of the reactant A. The order here is equal to 1 because you have 1 mole of this reactant A. All right, so for elementary steps, we look at the molecularity and we can look at the stoichiometry and be able to describe rate laws for those elementary steps. Second type of molecularity is bimolecular. Bimolecular, bi for two, implies that there's going to be collision, right? So in the reactant side, implying two species. All right, so this is going to imply that the reaction is going to be second order. Now, the two species could either be the same reactant, so two molecules of the same reactant, or it could be two different reactants, 1 mole of each reacting together. So here you have the example of a bimolecular reaction. You have 1 mole of reactant A reacting with another mole of reactant A. So that means 2 moles of the reactant A that gives product. This is bimolecular in its molecularity. It implies that there are two molecules that are reacting. And so when you look at the rate law for this elementary step, the rate is equal to the rate constant times the concentration of A powered to 2. So the reaction is second order. A second example could be that you have two different reactants, 1 mole of each reacting together. So reactant A reacting with a B, which gives products. Again, this is bimolecular because it implies two molecules, so two species that are reacting together. And so you could see that the rate here is expressed where the overall rate is going to be second order. The third type of molecularity is thermolecular. Thermolecular, thir here for three, right, implies that there's going to be collision here of three species. So this is going to be a third order. This is a rare step, meaning that it does occur, but rarely that we actually have collision of three molecules in a reaction. So here are examples. So you have here reactant A that reacts with another mole of reactant A and 1 mole of another reactant, which is B. So in other words, 2 moles of reactant A plus 1 mole of the reactant B to give products. This is termolecular because you have 3 moles of reactants. And so if you look at the rate law here that is expressed for this elementary step, you could see that this is a third order. You could as well have, 3 different reactants. So A reacting with B, that is reacting with C, that gives product. This is again termolecular. You have 3 moles of reactants. And so you could write the rate law here, and you could see that the overall order here is going to be a third order reaction. So this is how you could look at the elementary steps and describe rate laws for each elementary step. So when we have a multi-step reactions, often we have one elementary step that is much slower than the others. This step, which is the slow step, is going to be called the rate determining step. So the rate determining step which is the slow step, is going to limit the overall reaction rate, right? And we could look at an analogy here. So imagine you are driving on a highway, you're driving at 100 kilometers per hour, and then suddenly, there's a construction site, and so cars slow down, and then the rate of at which you're going to be driving is going to be dependent on the rate limiting section that is right here, right? So we could see in this picture that if you have a construction site, well, of course, the rate that you're going to be driving at is going to be determined based on the limit of the other cars that are driving in front of you. All right, so there's going to be a rate determining step, which is going to be based on the slow step. So we could say that a reaction is only as fast as its slowest step, so the rate determining step. So therefore, when we have a multi-step reaction, we need to look at the slow step, which is the rate determining step, and based on the molecularity of this elementary step, we could actually write down the rate law for the overall reaction. All right, so I'm going to show you an example on the next slide how we're going to be doing that. So we have to look at the slow step to be able to determine the rate law for the overall reaction. Now, here I put down the two requirements for a valid reaction mechanism. So remember that mechanisms are proposed based on the rate law that is determined experimentally, right? But when you propose a mechanism, basically it could be only valid if these two requirements are met. The first one here says that elementary steps in the mechanism must add to the overall balanced equation. This makes sense, right? If you have a multi-step reaction mechanism, you need to add up all the elementary steps so that when you add them, it gives you your overall balanced equation. All right. The second requirement is that the mechanism must agree with the experimentally determined rate law. Now, experimentally determined rate law, we already know we could determine this by using the method of initial rates. Now, how could my mechanism agree with the experimental rate law? Well, I'm going to show you on the next slide how we're going to do an example here, but basically we're going to look at the rate determining step, right, the slow step, and we're going to write down the rate law for that elementary step, right, based on the molecularity of that step. And if that rate law for the elementary step, which is the slow step, agrees with the experimentally determined rate law, it means that our mechanism is going to be valid. So we say that the mechanism is plausible or it's valid. So the first example we're going to do is a mechanism where our first elementary step is going to be a slow step. All right, so I took the same example that we had in the previous slide where we have hydrogen here that reacts with iodine chloride, gives you iodine and hydrogen chloride. And we have the experimentally determined rate law here, right? And we had a mechanism that was proposed. So if you guys remember on the previous slide, the mechanism was two steps. So you had two elementary steps. The first one where hydrogen reacted with 1 mole of iodine chloride formed hydrogen iodide and hydrogen chloride. Hydrogen iodide being an intermediate, it reacted with another mole of iodine chloride in the second elementary step. It gives us iodine and hydrogen chloride. So we have here a proposed mechanism. The question is the proposed mechanism plausible for the given reaction? So this is our given reaction. This is the experimental rate law. We want to know if this mechanism here is plausible for this reaction, okay? Now to do that, we need to know which of the two steps is a slow step. Right here, we're going to have a rate constant K1 for the first elementary step, K2 rate constant for the second elementary step. Now, we're told here that K1 is smaller than K2. So that means the rate constant for the second step here is actually bigger. If K is bigger, it means that the second step here is actually going to be fast step. and the first one here is going to be slow step. So the first step, first elementary step, having a smaller rate constant is going to be a slower step. So slow step here, which is going to be our rate determining step. Now, we're going to look at the two requirements that we saw in the previous slide, right? And we're going to use those two requirements to see if this mechanism is plausible. The first requirement was that if you add the two reactions, okay, so the two elementary steps, if you add these two steps, you should get to the overall reaction. All right, so if I add the two steps here, hydrogen iodide, which is an intermediate, is found as a product in the first elementary step, as a reactant in the second elementary step, so it gets canceled. And if I write down what I have left over, I'm going to have hydrogen gas with 2 moles of iodine chloride. That's going to give you iodine plus 2 moles of hydrogen chloride. All right, so we could see that by adding the two elementary steps, I get to the overall reaction. So I have here the same reaction, right? That is the one that is given to me from the beginning. So I get to the overall reaction. Now the second requirement is that when I look at the slow step, which is here in our case the first elementary step, I need to write the rate law and verify that this rate law is going to be the same as the one experimentally determined. Okay, so here, because the first elementary step is my slow step, so that means I need to write, so you have to write the rate law for the first elementary step. So basically this is going to be the rate is going to be equal to the rate constant K1 times the concentration of hydrogen powered to 1, because its coefficient is 1, times the concentration of iodine chloride powered to 1, because its coefficient is 1. So this would be the rate law for the first elementary step, which is the slow step. And if I look at this rate law, basically this rate law is the same as the experimental rate law. So based on that, we could say that the proposed mechanism is valid. All right, so the proposed mechanism is valid. So it's plausible. All right, so the two requirements are met. Now, this was the case for a first elementary step that was slow. What happens if your first elementary step is not slow, but is a fast step? All right, so we're going to see that it's a bit more tricky. So I'm going to show you here what happens when we're looking at mechanisms with the fast first elementary step. Right, so when you have a multi-step mechanism where the first step is fast, what happens is the products that are going to be formed in the first step are going to start to build up, because the rate at which they are going to be consumed in the next step is going to be limited to the fact that it's going to be a slower step. All right, so you're going to start generating products in initial step which are going to be limited by the rate of the next elementary step. So the first step, right, the reaction is going to reach an equilibrium because you're going to start making a lot of product. Now you're going to have the reverse reaction that's going to start to occur. Okay, again, due to the fact that you have a slower step that's going to be further after. So in a fast initial step, the rate law that's going to be predicted by the rate determining step may contain intermediates. So we're going to be able to use the fast step and its rate law to describe the concentration of the intermediates and what it corresponds to. We could, like I said, we could often express the concentration of the intermediates, right, by using the rate law of the elementary step that's going to be at equilibrium. So remember what equilibrium is, right? Equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. So if you have equilibrium, we're going to be able to use the concept of what equilibrium is and describe the rate law of the forward reaction, and we're going to be able to describe the rate law of the reverse reaction. Okay, so I'm going to show you how we're going to apply this in an example. So here we have another reaction. This is with hydrogen and nitrogen monoxide that forms nitrogen and water. And there's a mechanism that's been proposed, and we want to verify if this mechanism is plausible. First, they give us the rate law that's determined experimentally, right? So they tell us that the rate here is equal to a rate constant times the concentration of hydrogen times the concentration of nitrogen monoxide powered to the 2. All right, so this is a third order reaction. And the mechanism that is proposed is the following. So this mechanism has 3 elementary steps. The first elementary step has 2 molecules of nitrogen monoxide that react together. It forms dinitrogen dioxide. This is a fast step. Second elementary step, hydrogen, 1 mole, reacts with dinitrogen dioxide, right? So forms water and dinitrogen monoxide, which is a slow step here, the second elementary step. And then we have a third elementary step, which is that the dinitrogen monoxide reacts with another molecule of hydrogen, forms water and nitrogen gas, and this is a fast step. Now, when we look at this mechanism, we could see now that there are actually 2 intermediates in this reaction mechanism, right? So the first intermediate is dinitrogen dioxide, right? It's formed in the first elementary step and then it is consumed in the second one. And then you also have dinitrogen monoxide, which is as well an intermediate, right? It's formed in the second elementary step, and then it is consumed in the third elementary step, all right? So you have 2 intermediates here. Now, because the second step, right, is a slow step, what happens is in the first step, as dinitrogen dioxide is getting formed, because it's not being consumed in the second step due to the fact that it's slow, right, you're going to form a large amount of this intermediate, and now you're going to have the reverse reaction that's going to occur. So you're going to have this anytime you have a slow step. All the steps before the slow step are going to be reactions that are going to reach equilibrium. All right, so we're going to have what we call a rate constant K1 for the forward reaction, and we're going to have K minus 1. So we use here minus 1 to show that it's the reverse reaction. Okay, so that's for first elementary step. Second elementary step, we have a K2. Third elementary step, we have a rate constant K3. Now we want to see if this mechanism is plausible, so we need to look at the 2 requirements, right? So the first requirement again would be that you need to add up all the 3 reactions to see if it gives you the overall reaction, right? So you add up the 3 reactions. So the intermediates, of course, are going to get canceled, right? Because they're found in the reactant and product side. So if you add this, it's going to give you 2 nitrogen monoxide plus 2 hydrogen gas, which is going to give you 2 water molecules and nitrogen. So we could see that the overall reaction that we get is identical to the one that is given to us. So the first requirement is set. Now when we look at the second requirement says that we need to look at the rate law and verify if the rate law is the same as the one experimentally determined. So here the rate law is going to be based on the slow step, right? So this is the rate determining step because it's the slow step. And so that means that I need to use this step here to describe the rate law, right? If I do that here underneath, so it means that the rate is going to be equal to the rate constant K2 here times the concentration of hydrogen times the concentration of dinitrogen dioxide. Now, when I look at this rate law, I see that in my rate law, I have the concentration of an intermediate, right? And of course, we don't have intermediates that are expressed in our rate law, right? It's always concentration of the reactants. So I need to find a way to describe what this concentration of the intermediate is going to be equal to. So what I could do here is use the elementary step just before. So the fast step, that is the first elementary step, that's where I as well have this intermediate, which is the dinitrogen dioxide. So if I look at the fast step here, step 1, right, I could see that I could write a rate law for the rate of the forward reaction, right, which is going to be equal. So if I write here rate of the forward reaction is going to be equal to the rate of the reverse reaction. This is because my reaction's at equilibrium. So I could write the rate law for the forward reaction, and this rate law is going to be equal to the rate law of the reverse reaction. Okay, so let's do that. The rate law for the forward reaction is going to be equal to the K1, rate constant 1, times the concentration of NO, nitrogen dioxide, powered to the 2. Right, so basically what I'm doing is I'm looking at the forward reaction, right? This is the forward reaction, and I'm describing the rate law as if I'm looking at the forward reaction, right? So the rate of the forward reaction is K1 times the concentration of this reactant powered to 2, because this is a bimolecular molecularity. If I look at the reverse reaction now, well, dinitrogen dioxide is going to be my reactant, right, in the reverse reaction. And so it has a molecularity that is unimolecular. So that means I could describe the rate law of the reverse reaction as being K minus 1 times the concentration of dinitrogen dioxide. And basically, I can make these two expressions equal one another. Okay, so in this expression here now, I could isolate the concentration of dinitrogen dioxide, and once I isolate it, I could come and put it in this expression here. All right, so if we do that, if I isolate the concentration of dinitrogen dioxide is going to be equal to K1 over K minus 1 times the concentration of nitrogen dioxide, nitrogen oxide, powered to the 2. All right, so basically I could take this here and put it in the expression here. So this is going to be equal to the rate K2 times K1 over K minus 1. So I have a lot of K's here. Remember that these are all constants. All right, this is going to be equal, it's going to be multiplied by the concentration of hydrogen. It's going to be multiplied by the concentration of nitrogen monoxide powered to the 2. So if I rewrite this, in other words, rate here is going to be just equal to a constant, that's going to be K constant, times the concentration of hydrogen times the concentration of nitrogen monoxide powered to the 2. Now this is the rate expression that I would get for the rate determining step, right, the slow step. And I got this by actually using the concentration of the intermediate and its expression, and I got that again by looking at the fast step, right? So the elementary step 1, which is the fast step, I used that expression there for equilibrium and used the concept of equilibrium to isolate the concentration of the intermediate, and I replaced it in the rate law for the rate determining step. If you look at the rate law, this rate law agrees with the experimentally determined rate law on top here that is given to us, right? It's the same. So that means that the mechanism that is proposed to us here is actually plausible, right? So mechanism is plausible due to the fact that the two requirements are obeyed. So we do have um, the three elementary steps that are added up to give us the overall reaction. And when we look at the rate law for the slow step, the rate determining step, we could see that the rate law is the same as that of the one determined experimentally. So this is how you would look at fast first steps for elementary steps.